layers in organic soil, and they will be part of 3 different categories. They can be mechanical, electrical, and optical. And I will start with the mechanical one. So, in particular, I will talk about a technique called double cantilever beam test, and it is used to measure the additional strength of the solar cell. Especially, you're going to probe the weakest layer because it's the layer that is going to fail, and you're going to measure that one. Why we want to do it? Because we have flexible devices subjected to a lot of mechanical stress, both why we produce them and also why we use them if we move them around. So we want to detect what's the weakest layer and improve it. And we also want to understand the influence of the step factor on the structure. So how do we perform this experiment? We take a sample, then we perform an optional aging. We evaporate on top a protective layer. We normally use aluminum. Then we glue 2 beams on top of that, and we pull the sample apart that way, shown by the arrow, and we create a fractal samples, and we measure the energy that kept the sample together. So one of the samples that we have tested, it's what we call flexrod, which is basically our substrate, and it consists on the PET substrate. Then we have a negative electrode, which is a combination of PEDOPSS silver. Then we have the electron transport layer, which is the zinc oxide. The sample measures 4 centimeters times 1. And we also have done this experiment for same sample, but on top also the active layer, the whole transport layer, and the electrode, so the whole device. But for reason of time, I cannot show you all this. So we'll just focus on this one. So this is a picture of the 2 beams with in the middle of the sample. Then we need to remove those edges with the razor blade and apply 2 taps. And this is how it looks like. Then we mount the sample on the delaminator, and this is the sample. And this can move, and you can basically record the load that you need to move it. So what you obtain is a curve like this. We have the load versus the displacement. Basically, what you do is when you move your sample tensile, the load will increase until you reach a level which is called critical load. And at that point, your crack length, which is indicated by A, will grow, and then the load will go down. And then we move compressive, and then we repeat again this tensile movement, and we measure another value of critical load. And this way we obtain this curve, and we have a lot of measurement, basically, for one sample. And then we want to relate the critical load with the value of fractal energy using this formula. This is the fractal energy, PC is the critical load, A is the value of crack, left the crack, B is the width of the sample, equals with the plane strain elastic modulus, which is a property of the beam we're using, and H is half of the section of our sample. We want to test this sample under different aging conditions, and we use all these different aging conditions. They all last 24 hours, and we have, for instance, T, which is annealing. It's done at 85 degrees Celsius in a glove box and in the dark. Then we have a combination of temperature and humidity. It's done again 85 degrees Celsius, 45% relative humidity in the dark, and so on with UV, UV humidity, anneal UV, and anneal UV humidity. And now we look at the result. So what we can see from this is we have, first of all, we have here the fractal energy, and the x-axis we have the different aging with the N is the fresh device. And we can immediately recognize 2 groups. One has a very low fractal energy, one has a higher one. And we also have done XPS to understand where exactly the crack occurs. For group 1, we have the crack occurring between zinc oxide and PEDOPSS, and this is a picture of the PET side of the samples. While from group 2, we have a crack that is mainly between PET and PEDOPSS, and it will meander and moves also within PEDOPSS and zinc oxide. This is the picture of the sample. So we want to understand, of course, why this happens with some specific treatment. And we do this by looking at the XPS step profile. And what we notice is that we have basically a peak of circle which is pretty much fixed within our depth profile, and this indicates P.PSS. And then we have, we can look at the zinc, and we see that the zinc actually is not fixed, but it's changed. So we have a different diffusion of it depending on the treatment we are applying. And particularly, I tried to quantify this by calculating a ratio of the summaries of the count of the sulfur divided by summary of the count of the zinc. And what we obtain is that for fresh anneal UV immediate field, we have basically a high concentration of sulfur compared to zinc, while for the two treatments that actually had the highest factor energy, we also have the highest diffusion of zinc. So we clearly have a correlation between these two phenomena. And basically our device is stronger when we have a higher value of factor energy. This also relates quite well with the value of binding energy. And what we see is basically when we have more diffusion, we also have different binding energy, which actually indicates that we have some kind of bonding forming between zinc and sulfur. Quite interesting. So now I will move on the second part of my talk with talk about electrical methods. So there exists a lot of electrical techniques that can be applied for OPD. We have IV curve characterization, functions for the current, for the voltage, capacitance voltage, photosalics, etc. There are a lot. But in this talk I will focus on the impedance spectroscopy, which is the complex ratio of voltage versus current in an alternating current circuit. And also we measure this while evaluating the frequency. So in this slide I'm studying the stability of a cell, organic cell, which has ppcpm as the active layer. It's 1 centimeter square. I hope you are a bit familiar with OPD, otherwise I'm sorry. It's a embedded structure and encapsulated. And we use the constant current stress stability test, which is basically applying a constant value of current, and we use 70 milliamps per centimeter square, 100 and 150. And this is both done on the light and on the dark. And we use to monitor these impedance spectroscopies and also standard IV characterization. In particular, in this graph, I'm showing here the peak of the imaginary part of the impedance, also called reactance, which is plotted normalized. And in this other plot, I'm showing the short circuit current, also normalized. And what you can see immediately is that the short circuit current basically decay with time, this is time, seconds, quite steadily, while for the reactance, we see that they both increase, which is a sign of degradation, but in the dark, which is basically indicated by field points, they all tend to basically reach a similar value, while when we have light, we see that depending on which current we are using to stress the device, we have a different value of impedance measured. Of course, I mean, what happens is that when we have also light, we don't have only injected carriers by the current, but we also generate carriers, of course, from the light. And what this means is we are occupying different energy levels, and this could mean that we are probing different degradation mechanisms that are visible by we're looking at impedance, but not by just looking at the short circuit current. And we want to also apply this technique where we're using ISO standard for aging, and we're using 3 different ISO standards, 2 on light. ISO L2 is done at 1 sun, 65 degrees Celsius and a low % relative humidity. L3 is done at 0.6 sun, 65 degrees Celsius and 50% relative humidity. And D3 is done in dark, 65 degrees Celsius and 5% relative humidity. Here I'm showing again the imaginary part of the impedance shows a function of the frequency from 100 Hz to 1 MHz. And this is the fresh device. This is L2, L3, and D3. And with different color, I'm indicating different states of degradation of the device. When it's black, it's basically a fresh device. Then, for instance, blue indicates T80, which is when you reach the 80% of initial performance, and then so on with until the red color, which is T20, and it means that when you have reached the 20% of initial performance. And what we can see from this is that despite we have the same level of degradation, for instance T20, the peak is actually different depending on which frequency, which agent treatment we have used. And also the shift of the peak, as you can see, basically the peak is moving towards left, all of them, but it's different depending on which agent we are using, and we want to use this to understand better what's going on with extracting some parameters. And to do this, we use a model, and with the University of Padua, we have developed this impedance model for our organic solar cell. And as you can see, there is a very nice good fitting between the experimental data and the model. And by fitting, again, we can basically calculate or estimate each parameter that are present in the impedance model, then relate those with physical properties. Unfortunately, I cannot go too much in details for this, I just want to prove you the powerful of this technique and what you can do with it. The third and last part of my talk is the regard optical method. There are a lot of imaging techniques to image a device. We have X-ray diffraction, we have top sims, but in this talk I will focus on the TEM, transmission electron microscopy, and especially in the high resolution imaging possibility of the things. So the main drawback of a TEM is that you need a very thin cross-section, ideally below 100 nanometers. That can be challenging, especially if your device is very fragile. And normally what people have done, they have used focus ion beam to prepare the cross-section, which is a low technique, I would say, and also you can apply some damage due to the current you're using to read your sample. And we have used also ultramicrotromy, which is a technique that is normally used in biology to create cross-section of an organic device. And I would like to show you what the result slide. So in the picture on the left, you see the cross-section on the organic solar cell, which is represented here, with the sample created with fabricated with feedback. And on the right, we have the one fabricated with ultramicrotronic. Well, what you can see is that the both shows some layers, and the fig one shows that the structure is very intact and the layers are very defined, while the ultramicrotronic one shows that the structure is a bit wavy. That's understandable because we are applying a lot of mechanical stress when we are slicing the sample, and that's harsh for the device. But also it shows a lot of actually details. This, for example, is the zinc oxide layer, and you can see the nanoparticle of zinc, which we cannot see in display. And this also this is caused because our sample is also thinner, because we achieve a thinner sample with ultramicrotronic. And yeah, we can also start chemical information in the line scan, and this basically was used to relate with the structure that we assume we have. We also try to distinguish between CPM phase using actually energy filter PM, and this task is normally very challenging because CPM is above carbon-based material, and their contrast is normally very similar. It's very difficult to distinguish them, and in fact we cannot distinguish anything with the fig one. But when we do this with the ultramicrotronic sample, I don't know how much you can see, but it's possible to distinguish some phase. And if you set a threshold with ImageJ, for instance, you can try to analyze the particle domain size, and I obtain a domain of approximately 30 nanometers, which is pretty correct according to what we expect from literature. And also we can try to study the aging effect, and this is the same sample before aging and after aging, and you can see that it's very visible. We have something going on with the silver. This is the silver layer, and the silver paste in the organic soil cell, it's normally deposited from a paste, from an ink, which contains additives and solvent, and this probably reacts with the conditions that are in this aging environment, which is 50% relative humidity to 65 degrees Celsius and at approximately 1 sun. Basically concluding, I hope I show you that there are several techniques available for studying interface and also inner layers of 3D. And then if you combine mechanical, electrical and optical techniques, you can have a very good overview and vision of the effect of the degradation. And that if you combine the appropriate stress factor with the right technique, you can also try to address the effect of aging on the stability of the device. I'd like to acknowledge some persons that collaborate with me during the studies: Daska, Susan Geboya, Krebs, Nicholas Boston, Andrea Chester, and Susan Simonson, and thank you for the kind attention. Yeah, you look at this one or before?
That one, yes.
This is ultramicrotronic. Yeah, sorry. Yeah, good question. It's a good question. We haven't done it. The reason why I thought it wasn't that important to do it because we saw so much more details in the ultramicrotronic one. So I was hoping that to see actually more also on the inner layers. Like for example the phase separation, but it was not visible. We only saw the silver, and yeah, it didn't motivate me enough to keep it for the other one. But good point.
There is a comment online. They say very interesting. They would receive a PDF file if possible. Would it be possible?
Yeah.
Thank you very much. Right. Also reference to published article, but we will share by email.
Well, some of the things are not published yet, and so they are not paper yet, but they're coming. So,
okay, but we will share by email. We will share by email.
okay, maybe